So the various combinations of acids and bases that we can titrate are strong acid with a strong base. We could do a strong acid with a weak base, and we could do a weak acid with a strong base. So those are the three different scenarios that we're going to go through. The one that we're going to go through today is a strong acid with a strong base. So the general reaction would be HX plus MOH makes water and the salt MX. So for example, a strong acid could be HCl, the strong base can be sodium hydroxide, and that would make water and sodium chloride. Now we want to walk through the what's going to be in the flask during various points in our titration. So we're going to put sodium hydroxide in our burette, and we're going to have the HCl as our analyte. So this is our titrant, this is our analyte. In this case, we actually know the molarity of both of these. Just for our purposes, we're just more interested in what's in the flask at various points in the titration, before, during the reaction, at the end, and after the end. And we're going to look at what the graph of pH over volume of titrant added, in this case the hydroxide added, would look like. So the pH probe is sitting in the flask right here. So I did little drawings. That's the best pH probe I got. Okay, so before we add any sodium hydroxide into this flask, what's in there is the, in this case it's HCl, but I just want to do generic. I'm just going to refer to it as HX. In our example, HX is HCl though. And so essentially, if this is a strong acid, X is pretty much a spectator ion. So you can treat this as if it's just simply hydrogen ions. So at the molecular level, every single molecule is broken up into its ions. And of course, there's water in there as well. There's going to be water throughout here. But it's mostly that strong acid. So how to calculate the pH? We can get the molarity of the hydrogen straight from that strong acid and just take the negative log of that. Okay, now, so the pH is going to start pretty low. So let's say this is 7 right here. The pH is going to start pretty low because it's just acid. It's just strong acid. So start below 7. Okay, now we're going to start dripping the sodium hydroxide in, not until the reaction is completely done, but kind of like halfway. So we're going to put like about half of the base needed to neutralize about half of that acid. So if you think about what is your limiting reactant, it's your sodium hydroxide. It's your strong base. And the excess reactant is your HCl, the strong acid. So if we're not at the end point yet, all of the sodium hydroxide will get neutralized. So that won't be present. Even though we're adding it, it gets neutralized, it gets wiped out because we have a lot of HCl in there. But what's still going to be present is the extra HCl, which we're referring to as HX, and the products as well. We're starting to make some of the products. So we're going to make water and that salt. In our example, it's sodium chloride. Okay, so what we're going to see is still that strong acid still there, but it's not all there. We're going to see, of course, water, but I'm just not going to show that. And then the salt that we make. Now, what's really going to affect our pH at this point? Well, it's still just a strong acid. Recall that some salts, yes, are acidic or basic, but not conjugates of strong acids and bases. Those are always neutral. And this is the conjugate of the strong base, and this is the conjugate of the strong acid. Those are 100% neutral. So we simply just have a strong acid in this situation. So we're going to solve for the pH just like we did here. But of course, the pH is rising because some of that acid is getting neutralized. So you'll see a rise here. So that's like during. So this is before, this is during. Okay, now at the equivalence point, that means we have reacted away all the acid with the perfect amount of base. So at that point, we have only products, water and our salt, the sodium chloride in this case. So remember, water is neutral, and this salt is also neutral, such as sodium chloride. Conjugates of strong acids and bases are always neutral. So at this point, the pH should be just 7. There's no calculation needed here. And what this would look like on our graph, the pH would just fly up. And so I'm trying to show that the equivalence point right here is going to be at 7 exactly. So once all the acid's wiped out, the pH just shoots straight up very quickly. All right, now let's say you didn't close the valve right away and oops, a bunch of sodium hydroxide just dropped into your flask. So we'd show after the equivalence point. Now, after the equivalence point, there's no more acid in this flask for the sodium hydroxide to neutralize. It's all wiped out. So we're gonna have just extra sodium hydroxide floating around. We still have our products. We have that extra sodium hydroxide. In this case, we're calling it MOH, the generic form of a strong base. So that's what's going to be present. And since it's a strong base, all of its hydroxides will come off. So how we find the pH at this point? Well, you can figure out the concentration of hydroxide based off of any extra left over. And from there, we'll find the POH when we take the negative log of this. And then from there, we can find the pH. So those will be your steps. All right, so this is these are just some example math questions associated with it. What I really want us to super focus on is what is present at each point. Oh, I forgot to add this. Okay, so after the equivalence point, we're adding the extra base, so the pH just shoots up, and this is just going to be the extra hydroxide that we added past the equivalence point. It's going to steady out around 14 if we add a lot. And that's what our graph will look like. Okay, so for example, if 100 milliliters of 0.1 molar hydrobromic acid was titrated with 0.1 molar lithium hydroxide, what volume of lithium hydroxide would be needed to reach the equivalence point? So the equivalence point is like the perfect mole ratio needed. This is a strong acid and this is a strong base. You guys still have to have those memorized. So let's write a reaction. You should find that these will react in a 1-to-1 mole ratio. So I can answer this question just by thinking about the 1-to-1 mole ratio and the fact that these are the same molarity. So if they react in a 1-to-1 mole ratio and if these solutions are with the same exact molarity, that means they're going to take the same amount of volume to reach the equivalence point. So I will need 100 milliliters of lithium hydroxide to reach the equivalence point. You could also prove that to me by calculating the moles of HBr present here. We'd have 0.01, and then with this mole to mole ratio, that means the moles of lithium hydroxide present is also 0.01. So if we set up a molarity equation with the lithium hydroxide and solve for liters, you should get 0.1 liters, which is 100 milliliters. So again, you could have answered that knowing it's a 1-to-1 mole ratio, and if we're mixing equal concentrations, then the equal volume should reach the equivalence point. Now, at the equivalence point, how are we going to find the pH? Well, at the equivalence point, we have products only. And so the identity of your product determines the pH of the solution. My products are water and lithium bromide. Now, if you think about lithium, that is the conjugate to a strong base. That will be neutral. bromine is the conjugate to a strong acid. That will be neutral. So we have completely neutral products. The pH will be 7. Now to determine what indicator you're going to choose, you want an indicator that'll change color around a pH of 7 so you know when to stop the reaction. So if you guys look at the back of your homework at your indicator list, there's bromothymol blue, who can change color between pH of 6 to 7.6, so that would be a pretty good option. Cresol red is probably, it's pretty good too. Okay, the next couple questions are kind of more so of a challenge. You're asked to do them in your homework, but they're more so like bonus questions. I expect you to describe how to calculate the pH, but actually nailing the calculations is a lot of work, and that would just be like kind of like a bonus question. So what is the pH of the solution after 20 milliliters of lithium hydroxide was added? Well, if you think about this, this is during the reaction because we haven't added all 100 yet. If you only added 20 milliliters, you're not quite at your equivalence point. So that means some of the acid will get wiped out, but not all of it by the lithium hydroxide. So, so we're going to have, it's going to be a strong acid solution still because, like I said, not all of it was wiped out. So we'll go about solving for the pH by taking the negative log of how many hydrogens are left, but we got to figure that out first. So let's see how many moles of HBr were present. We had 0.01 moles of HBr total at the start. But some of those got wiped out. So let's figure out how many moles of lithium hydroxide were added. Now I can drop the lithium because it's a spectator ion, because it's neutral. So I'm just doing that. All right, so if I had 0.01 moles of the acid at the start and I dropped in this many moles of base, that means due to the 1-to-1 mole ratio, this is the same amount of moles of acid that get wiped out. So we have, wow, mental math's not my strong suit right now. 0.008 moles of HBr left. Okay, now that got diluted down. So again, we're trying to get the pH, so I want the concentration of hydrogen. I need concentration, not moles. So this isn't 100 milliliters anymore. Currently in that flask, it's 120 milliliters. So I have to divide that by 0.12 liters to get my concentration. Okay, so technically that's the molarity of the acid, but this is a strong acid solution, so we can assume that all of these H's fall off. So the concentration of hydrogen is also 0.067 molar. From there, we can find the pH by simply taking the negative log of that. Okay, so it was, before we added the sodium or the lithium hydroxide, for a 0.1 molar solution, it would be a pH of 1. So you can see it rose a little bit because we added the base and some of the acid was neutralized. All right, for the next question, we're going to add what is the pH after 130 milliliters was added? Okay, this is beyond the equivalence point. So we have extra base and all of our acid is gone. So, so we have a strong base solution. So we got to figure out how much extra lithium hydroxide was added. Now, I know that if 100 milliliters of it was wiped out because it was neutralized by the acid, that means 30 milliliters of that is extra. It didn't have any acid to react with. So that's our extra base left over. So let's figure out how many moles of lithium hydroxide were in that 30 milliliters. It would be 0.003 moles of the lithium hydroxide left as extra. So to get the molarity, I need to divide that by the total volume at this point in time. It's a mixture of the 100 milliliters of the acid with the 130 of the base. So that would be 0.23 liters. So we have a molarity of 0.013 molar lithium hydroxide, which remember is a strong base. So all of those hydroxides will dissociate in the water. So the concentration of hydroxide will also be 0.013 molar. Now if we take the negative log of that, since that's hydroxide, of course that's POH and not pH. So subtract 14 from that and we can get our pH to be 12.11. That makes sense because we have extra base. This should be a basic solution at this point. That would be up here on the graph in that section. Okay, so now you guys should be able to predict the outcome of a strong acid, strong base titration. You guys have the rest of this hour to work on your homework. The answer key is posted. You guys should be able to work through all of salt hydrolysis and buffers.